Okay, so I guess you guys enjoyed having the last couple of days off.
Oh, we're this Tuesday.
Yeah, I enjoyed that hour and a half off from lecture.
I didn't have class at 2:30 that day.
Sweet.
Did you know?
I was out at the Broadband Wireless Access and Application Center spring meeting through the National Science Foundation up in at University of Notre Dame. So we were trying to collaborate on a lot of some really neat stuff was coming in. What we're potentially going to be doing is we're going to be building a new engineering research center that we'll be working with Arizona, Notre Dame, Virginia Tech, Virginia, and Auburn, and trying to build a Google Maps, but specifically for spectrum sensing. And spectrum sensing has become important because as more and more people get smartphones and laptops and little chips that they're using for Fitbits and running all over the place, the actual wireless spectrum is becoming more and more jam-packed. So spectrum sharing becomes an interesting challenge. Like, how do you actually try to get multiple people to get through the spectrum at the same time? So we're going to be trying to put up a new kind of Google Maps to indicate what groups, what types of spectrum and how much spectrum is being used in different places. And the reason why it's kind of important is because it's different. It's a different challenge in New York versus, say, Oxford, Mississippi, right? So being able to do that and being able to come up with the efficient method of trying to help get as many people online as possible becomes helpful, especially if you're at a football game and you want to send a text to somebody. Ole Miss scores a touchdown, hotty-toddy, woohoo. Like, I want to send a selfie or whatever, right? And you have to then wait an hour to send it because it's all jam-packed, right? That's part of the spectrum sensing problem. Now, at the CMOS level, this becomes interesting because all the spectrum sensors have to consume lowest possible power. But they want it to be super high performance because it has to be massive in, massive out, MIMO. Right? You have to have some sort of orthogonal frequency division multiplexing. So you have all kinds of challenges that work down from the CMOS level to the architecture level, to the system architecture level, to the wireless network level. So you guys can, as this is building up, hopefully we'll be creating a number of PhD positions in this kind of thing, and more interdisciplinary challenge. So if those of you who are afraid to go to the real world are no, but more, yeah, right, Kevin? I was there. No, I mean, well, more importantly, if that's the kind of thing that you want to end up doing with your life and being a PhD and kind of pursuing those kind of jobs, we're working on that, creating more opportunities for you. So that's where I was. I briefly looked over the lab submissions. I haven't had an opportunity to go into them in too much detail. I know at last Thursday I did say don't try to spend too much time on it. If you're running into errors, just try to document your troubleshooting. And some of the groups still wrote, spent 20, 30 hours on the projects. Like, well, I gave you an out on that one. It's, take us what you will. And the another important thing is I call this the better is the enemy of good enough. And what I mean by that is if you're trying to design something, in the lab it says design a full adder. It does not say design the most optimized full adder of all time. Just get it in there, get it working, right? So if you spend too much time, I mean, this is just an example of that one group emailed me, but if you spend hours and hours and hours and hours trying to optimize it and get it working, and then the deadline comes up and you don't have a working full adder, well, that's all well and good that you're working on optimization methods, but you never address the initial challenge. And as engineers, we have to fight this, right? Because in our heads, we're always trying to look for the best possible solution. And eventually, you have a customer and they want it to actually just work, right? So if you don't get it working, it doesn't matter how good your optimization methods are. So this is one of these challenges that you probably should kind of bear in mind, especially when you're dealing with a final lab, which I don't think is too time-consuming. And then I did read there's some feedback from you guys on how the lab write-up is improved. So by next Tuesday, just like I did for Lab 1, if you saw, I did update the Lab 1 write-up based on your feedback. I'll do the same thing for Lab 2. And I will also, by tomorrow, have my feedback on your drafts of the presentations, because those start Tuesday. I believe 4 of the 5 semi-wikis are posted, and there's been a variety of comments. One of them doesn't have any comments at all. One of them has like 10 or 12, and keeps growing and growing. Suprop, since you're the last group that hasn't been posted yet, I was going to have 4 groups present on Tuesday, then Thursday I was going to have 1 group, and then Kevin present on Thursday while the pizza's there. So to give you guys more time to prepare, you'll be the group on Thursday. Okay. So does anybody have any questions before I move on to? Yes? I just saw a bunch of people laughing. I was like, oh great, what happened? Okay. So anyway, does anybody have any questions or concerns before I move on? Okay, so we are officially in the last stretch. This is the last lecture for Lab 3, and this is the last lecture that I will be giving this semester. So we're going to be talking about, at this point, we've gotten everything from building it up from the transistor level to combining everything into developing logic. We learned SPICE, we learned Verilog, we learned optimization methods, RC models, wiring, then taking everything and building, you actually put it in, do a layout, do layout, you do testing, you do then selective flattening to be able to try to optimize the layout, you do all these floor plannings, and then once you get all this stuff, then you start worrying about this concept of I/O and power planning. I/O, eventually you want to design a chip, but you need it to actually do something that produces results for the person using it, right? So that's where I/O comes in. So we have I/O and electric and mechanical. This is their pad frame, which we learned about we're about to learn about the pad frame, with what's actually going on inside of these pads, and how we actually use that to reduce static shock and translate the input and output signals to your chip. So this is the actual layout of the chip, and so it's down here. So now you're trying to optimize the sizing. So you have a number of inputs and outputs, right? And this is kind of just a general layout. Yours, as we discussed last lecture, I showed you, is it somewhere in here? Yeah, I showed you the layout of what the MIPS looks like. Or is that in section 8? I guess that was section 8. Okay. Here we go. So anyway, what this is involving is you're actually going to be building something called a chip package. So that involves and so these are down here as are examples of chip packages where you've worked with these in like digital systems and and electric circuits where you have a DIP and you at the top it has the little oval, semicircle, and it indicates which one's at the top and which one's at the bottom. And the reason why is because you have to keep track of which ones are the input pins and the output pins. So you have some sort of small 40-pin DIP or 14 DIP where you're actually trying to use it to do some sort of this is an adder, or this is a multivibrator, or this is some sort of circuit that's in there to prop to the function that you need, right? And so you use that to lay it out. So now this is actually going in here. These pins relate to your pad frames. So the chip package provides a mechanical and electrical connection between the chip and a circuit board. So you're putting this into the circuit board as you've done before in previous classes. The electrical connection is signals and power from the chip to the board. So you have little delay or distortion. This is an important goal. As we now know, we have to deal with clocking zones, and you have to deal with noise margins, right? So you don't want it to delay. You want the input signals to actually properly reach the 0 and 1 regions as we've calculated. Mechanical connection chip to board removes heat produced on chip. This becomes important because as we now know, if you have too much heat, you could potentially, especially when you're dealing with the Miller coupling factor, you could potentially, especially when it switches, you could potentially change the logic on the wire, which then creates problems in your calculations. Protects chip from mechanical damage, and we'll show you an example of that here a little later. Compatible with thermal expansion and inexpensive to manufacture and test. So, unlike the first lecture, I described that when you're synthesizing chips, like the first few can be very expensive. but as you get to 10,000 or 100,000, it becomes very inexpensive to manufacture, right? And the reason why is after you've gone through the whole process, as we've covered in section 9, of floor planning, and testing, and layout, and, as we now get here and we're testing them, once you get a successful test and you know that you can meet the yield every time, it becomes very inexpensive to just mass produce the chips. So, as I was kind of explaining, here's some programmable gate arrays, some DIPs, and these are all chips that are used within the chip package and contain the pad frame, right? So all of these, so here you have 296 pins, 387 pins. Typically what we've been using, what you'll be doing in your lab 3 is a 40-pin pad frame, and that's 40-pin is typically conventional, right? So, and I think there was a 40-pin DIP. Yeah. So you're building something like this, right? This one here. So this one, and this is actually the diagram you'll see at the end of the lecture today. Everything that you build up into CMOS up to this point is this chip here. So then it has to connect to your pads, your pad frame, and then from the pad frame, it's going to go through the pins to your circuit board. Okay. So let's formally define pad frame. The pad frame is the organization of the metal pads into a ring around the peripheral of the chip. And so we have two types of limitations on how we can design the die. Now, as we decided, we had the die is the space in between, right? So you either have the core limited die or the pad limited die. In this case, technically what you're doing in lab 3 is a pad limited die, though the design that you're coming up with is not going to push the limits of the pad. The pad limited die, the number of pads determine the die size. So when you do your final layout, the pads are going to be significantly larger than the actual chip, whereas in a core limited die, the core logic determines the die size. So if you're going to have something like a PGA, right, that's going to be significantly larger than the pads, you're going to try to have that as a core, it's a core limited size. But if you're using a PIP, you have a very tiny core, so it's going to be limited by the pad frame. So that's the difference. And how that impact and how each one of those is done impacts the actual size of the chip. So here, I'm going to disguise what all these corner and bonding pads mean. But basically here, in this circuit, where you have VDD and VSS, so you have VDD and ground. So we're going to be also dealing with power pads, which how do we actually regulate the power consumption in the chip. And a lot of these I/O pads are going to have specific I/O signals, right? So let's say you're trying to MIPS processor, right? If you recall from 385, we used files to have input signals go to the program counter, to the registers, and to the data memory, right? So what you have to do here is you actually have to load that information to the chip somehow. So the compiler, what it's going to do is it's actually going to load the signals into the pads, then it's going to go to the program counter, so you're going to have a signal, say, write to PC write, reg write, and then mem write. And you're going to use those to actually indicate in which specific registers in memory how you're going to update that information so you can start your program. And then your outputs are going to be once you've reached the point where you've had run all the code in the instruction memory, it has to send a signal back to the operating system indicating that everything's complete. So do I keep everything in the low-level memory here, or am I going to take everything out of that chip and then go to the non-volatile memory? So that's where kind of your I/O signals and your control signals, and then you have to regulate everything with your supply voltage, and we're going to talk about power pads and pad rings here in a second. So is this all making sense? All right, so the pad and diagram here, I'll formally read this and then I'll zoom in and describe the actual diagram. A metal pad
which is each individual pad in the pad frame, is a set of gold bond wires used to connect a chip to the package. Really quickly, this is kind of a description of the bonding pad. But here's what's going on. So you have this bonding pad that connects to each input, right? And so we're describing this pitch, and we have the electrostatic discharge for PMOS and electrostatic discharge for NMOS, right? And then we have pad logic. So pad logic is kind of breaking down how we actually use the sequential logic to actually buffer the information. And each pad is going to be different. Sometimes you just want to buffer the supply voltage. Other times you actually want to control the timing of the input signals. And we'll go over an example of that a little later. So then you have electrostatic discharge transistor for NMOS. So what happens is, let's say you get, somebody has some charge, like when you rub a balloon and your hair gets really big, or you zap your finger on the pad. If you do that to a chip, you're going to destroy the whole chip, right? So I think it's not the next. It's the problem down here, but I'm going to lead to why that's important. So the bonding pad is just the definition. It allows a connection between the wire from the circuitry to the pad frame, right? So basically, it's connecting back and forth. You have your pin, and first thing you do is you have your bonding pad, then you have electrostatic discharge for PMOS, and then you have your pad logic, and then you have your electrostatic discharge for NMOS. So you have your bonding wire, which you guys have been working on. It connects to your metal. Then you have your oxide, like we've learned about in your silicon substrate, which we've learned about all the way back in section 1, right? So this is kind of a general overview of what the bonding pad frame is. So now, the next thing we're going to deal with are these electrostatic discharge protection circuits. And so this is actually uses a limiting resistor, right? Let me use my editing here. Cancel. Which one was it? Comment. Oh, here we go. Okay, so first we have our current limiting resistor, right? And so, in diodes, large enough to sustain significant current in order to prevent shock to the CMOS gates. Right, so we have some thin gate oxides relating to an inverter. So here we've had our bonding pad. So if we're going back here, we have our bonding pad. And now we're going to our ESD PMOS, right? And then we go to our logic, and then doing the same thing with NMOS, right? So what's going to happen here is we could potentially get a very, very high voltage based on electrostatic discharge. And I want to show you this example to kind of go on how bad this can get. So consider the charge on the human body discharged at a rate of 10 microamperes for 1 microsecond to a capacitor of 0.2025 picofarads. How much voltage is applied to the pad frame? So if you recall from TGO 2.3, your time is equal to the time for discharge is the capacitance divided by the current times the voltage. So we rearrange the voltage, time is equal to current divided by capacitance. So the time was 1 microsecond. The current was 10 microamperes, 0.25 picofarads, and that comes out to 400 volts. So if you designed a circuit that's supposed to work with a noise margin of 0 to 3.3 volts, right? So that would be 0.6 micron. And then suddenly you shock it with 400 volts, you're going to fry the circuit, right? And that's very common. You zip, touch it, it's gone. So that's why, going back up here, that's why having these circuits in there is important. So you have a very strong limiting resistor. So you have some sort of voltage, right? So let's say you get 400 volts, and you want to. So what you want to do is you want to limit the current by dissipating that voltage in the resistor before it ever gets into your circuitry. Right? So that and the diode clamps, that's what's going to work here. So you have VDD and ground in your. So here you have the flow to VDD. Here you could have the negative flow to ground. So basically what you're doing is you're dissipating the energy, and then you have it flow to VDD and ground without having to worry about
going to the circuitry. That's where the power frame that I was telling you about comes into play.
So let me formally define 9.22. Electrostatic discharge protection circuits use a current-limiting resistor and diodes large enough to sustain significant current in order to prevent shock to the CMOS gates. And so I've gone over example 9.2, but this is now important because what we're trying to do is we have this electrostatic shock, and we're trying to prevent it from getting to the circuitry. We now know that even if it's on just this much current, 10 microamperes for only 1 millisecond. So that's not very long, right? 1 millisecond. And 0.25 picofarads, that's 10 to the negative 12. We're still getting to 400 volts. So something that's not terribly significant. But if you have a shock and it goes for a much longer amount of time and much more current, depending on how much static discharge you have in your system, you could really fry the circuit. So that's why we have to worry about power pads. So we're going to use those for VDD and ground, and we're also going to use this power ring that's going to run around the circuit in order to supply the voltage to all of the I/O and be able to dissipate it. So we're going to formally define power ring as running around the pad ring. So you're going to have your power ring running around here, right? So it's supply voltage to the I/O pads only. Another set, VDD VSS pads, connects to a second power ring that supplies the logic core. So that's why, if you don't mind, I'm going to zoom back up here for a split second. If you recall here, we have separate supply voltage. So this is VDD and ground, VDD and ground. So this is the core logic. This is the power supply. So you have different I/O pads as opposed to just the power ring that supplies the logic core. Does that make sense now? And as you can tell, the difference between having to supply it to the power pads becomes important because we have to worry about this electrostatic discharge, as well as the core logic in between the ESD for PMOS and ESD for NMOS. Okay, does anybody have any other questions before we continue? I probably should, yeah. And so what we're kind of talking about here is our hybrid pad and core limited frames. So sometimes if you have these corner pads, so here it says 2-pad, corner pad, format, changer, core limited to pad limited. So you have all of these I/O pads, these power pads, and then you have to worry about the corners. And if you recall from last lecture, that when we try to do the floor plan and we're setting it out, we use these algorithms to try to find ways across. So then we have to worry about what we're going to be routing power around to get to. So we have some here and here, so that we have our we have some core logic there and there, so we can optimize the area, right? So we have to worry about the core pad, the corner pads, being able to route the power and route the signals around appropriately. This is where that kind of issue can take place. And we're not going to be really going into pad frame design. Generally, in this level CMOS course, you're provided with a pad frame, as you will be in your lab. But it's kind of important to know that you should, if you're going to use a pad frame, you should at least have a general idea. This is a pad frame, and these are things that are being done. Like when I took CMOS, we never bothered to go into a pad frame other than this is a pad frame. So I wish I had learned more. Like, this is a pad frame. You have to connect things. Okay, good luck. So this pad layout logic is kind of what I was talking about here. So you have a supply voltage. Here we have some sort of data out that's going out from the
from the circuit to the pad. We have supply voltage and ground, and we have to have some sort of signal dissipation in here, right? Because we ultimately want to worry, we don't have to worry about electrostatic discharge. We have to learn about power regulation. That becomes very important. So here you have an inversion, and then it gets inverted again, and then goes out to the pad frame, right? So the pad layout logic uses an internal tri-state buffer, tri-state buffer, to regulate the control signal. But this is not an inverter, this is a tri-state buffer.
So you have typically tied to VDD, so that means it's going to be working. As we remember from 385, a tri-state buffer, it's 1, it passes the signal. If it's 0, it holds it. So there would be some sort of signal here that could be used to block the flow of the signal if for some reason there was some sort of situation where potentially you could fry the circuit. Does that make sense? So your electrostatic discharge, kind of the overview, you have your pad, right? And from there, you're going to go to your ESD for PMOS. So ultimately what you're trying to do is you're trying to use that regulation resistor. You have those large diodes that are coming out to try to dissipate some high current. Then you have your pad frame logic that uses your tri-state buffer. Then it's going to go to the NMOS electrostatic discharge and then to the output. So that is, so in all of these pads, you have in your pad frame, that's what's physically going on. So hopefully you at least have a general understanding what's going on in each pad and what that pad frame it entails. Okay, before we get to tape out, does anybody have any questions about the pad frame and the I/O power pads? Huh? Right, so let's formally define tape out. It's the final verification task performed before the design database is shipped to the foundry. So you've designed all of this stuff in Spice, or in Verilog, or in your layouts. You've designed them, you've tested them, you've verified them. You've laid out, you've done your floor planning algorithms, you've optimized the area, you've done all this stuff, you've done all your work, you've done all of your power calculations. Now you have to do these final sets of tests called tape out before you can then send it to foundry. For example, Moses, right? Before you send it off to Moses, you want to do this final set of tests. So you're doing your DRC or ERC or NCC checks, right? And then you're doing tape out. So you have to worry about these design corners, if you recall, right? Has to be functional. It has to pass DRC and layout versus schematic. Okay, so you guys dealt a little bit with layout versus schematic in Lab 2. Tape out classification is designed so you have a digital tape out, which is what you'll be dealing with. But if you're doing more of an analog type circuit, you could do an analog tape out as well. System on chip and micro electrical mechanical systems, which are outside the scope of this course. Right? What we're going to be dealing with in this next section is the digital tape out, because it is digital CMOS VLSI course. So we've also learned about system on package, system on chip, wire bound package, and flip chip packages. Well, we haven't really gone into flip chip packages very much in this course because it's not really digital CMOS. So in order to, did everybody get 9.26? All right. So there's 3 major tasks for tape out. Chip assembly, which is what you guys have been dealing with a lot. Seal ring generation, which we're going to take our chip and we're going to enclose the die to basically try to keep it from getting wet or try to ensure that electrostatic discharge doesn't become a problem. So this becomes a seal ring, right? So if you recall, you have a hard drive. If you open it up, if you're not in a clean room, you've basically destroyed it, right? So you can think of the seal ring as the CMOS equivalent of the hard drive cover. And then chip ID, revision ID, hardware verification generation. So what you're doing is, and this in and of itself is an entire field, trying to ensure security and reliability. What happens, this is a common issue for Department of Defense research. What happens if you contract out your hardware design to a Chinese company and they install a hardware Trojan which leaks all of your information to a side channel, which then gives all of your information to the Chinese government? So there's an entire field based on this, that's, and this is talked about a lot at the Design Automation Conference, where basically you're just checking to make sure that there's no hardware Trojans and you're promoting and preserving intellectual property. But first, the seal ring is a structure used to enclose the die outside. Okay, so I basically just described this, but let's formally define it. A seal ring is a structure to enclose the die outside of the pad frame, which protects the die from moisture and sawing. Also contains scribe, which is where to saw the die. So ultimately, you have a number of dies that you're putting in one wafer, right? And so the seal ring is basically going to say cut here, cut here, cut here, cut here. You don't want to cut in the middle because you're breaking the chip in half, right? And so ultimately, what you're doing is you're taking the seal rings here, which is this. I actually can zoom in on this picture. This is a really good example here, right? Right. So this is a good example here, right? So you have here you can see you have a corner pad, right? And then what happens is you're actually going to have a seal ring here, which says if you cut here, you're going to be fine. You're not going to get anything there. It's going to keep all the moisture out, so it doesn't interact with the pads. And you're actually using all of this to try to do some of your electrostatic discharge. So this is kind of the start of the ESD logic here. So this is where the seal ring occurs. So sealing it up, that becomes an important part of the tape-out process. All right. And so we have tasks that we're doing here. Equivalence checking sign off. Now, you design stuff in Spice. You design stuff in Verilog, or you did it in VHDL. You've done your layout versus schematic. Equivalency checking is kind of using your testing to determine whether or not your circuit actually does what you intended to do, right? That's ultimately your goal is to make a circuit that does something. Right? So the equivalence checking sign-off is verified with the final gate level net list. So you're taking something from Verilog or VHDL, you're sending it down to HSpice or PSpice or whichever tool you're using. In this case, you're using WinSpice. It has the same functionality as the source RTL. So you register transfer language, and your final net list should work. And they should do the exact same things. So same inputs, same outputs, right? So and if you and this becomes important because in Verilog and VHDL, you can synthesize it to an FPGA, like you're doing with 86. Whereas if you're doing it to a system on chip or CMOS, it's going to synthesize it in a very different way. Because you're not worried about programmable logic arrays. You want to optimize power consumption and area. But you want to make sure that your synthesis method generated the exact same logic. So this is where the TGO ends, but also multiple checks must be performed. Equivalence checking, like we just did, structural checks. Is it actually structurally sound? Is there any issues? Are all the wires together? Are all the logic working? Cross-clock domain checks and power domain checks. We kind of briefly talked about it, where we talked about different voltage domains. And you have to make sure that you've properly wired up your voltage domains properly to ensure that you can propagate the signal through. And then timing and signal integrity sign-off. Not only does it work, but does it meet all the timing and signal constraints that you set? Remember, we want it to work at a certain power and performance. And we want it to work at, for example, when I was in CMOS, we were designing a digital thermometer, and it had to fit inside the pad frame, and it had to work at 1 kilohertz, right? So so that doesn't sound like much, and it really wasn't that much. There's just ultimately trying to get people across the finish line. But if it doesn't work at 1 kilohertz, it doesn't meet your timing and signal integrity checkoff. Now, if you did design it properly, it would still work at like 12 megahertz, which is better than 1 kilohertz, obviously. But
the key thing is you want to test all your design corners, and so let me do this formally first before I go into this. Use to test at PVT design corners for hold and setup time to test for functionality and performance. So we're talking about sequential logic where you have to deal with a lot of hold times and setup times, and you have to worry about contamination delays, and that becomes very important, especially when you're considering different designs. So in section 6, in fact, you did a whole problem about this on the exam. It's how do you second exam where you properly design. You had an ALU and you had some multiplexers and you had a sequential circuit, and you had to take all of this. The timing and signal integrity sign-off means that you have tested this and it works. And then kind of intuitively you can figure out probably what power sign-off means. It's used to validate active power budgeting. So we talked about in section 8, you have to worry about power consumption at different portions of the circuit. You don't want it to get too hot, otherwise you could potentially damage the circuit. To check dynamic power consumption and average power consumption across all timing and power corners. So you have specific timing that you're supposed to meet, and does it actually consume the amount of power that you claim it does? So basically, this is just a fancy way of saying, does it do the logic I want it to do? Does it run as fast as I want it to do? Has it consumed as much power as I claim it will? Does that make sense? So this is all part of the tapeout. So everything you've done up to this point, now you're just proving that all this knowledge that you have in your head from CMOS actually worked. Right? And so I kind of briefly touched on these. I don't want to go into too much, but like you have your active power consumption, you have you're worrying about switching factor, and you're making sure that certain portions of the circuit work and about what you expected, right? So your switching factor means that you have some sort of prediction on average on how much your code is going to perform load byte and stored byte operations versus ALU versus branching versus jumping. Right? And that all goes into switching factor calculations. It all ultimately goes into Amdahl's law, right? So you use Amdahl's law to try to reduce your average power consumption by calculating switching factors. Now, leakage power must be performed across all the design corners. So basically, what leakage power means is that you have power consumption that's not actively contributing to the logical calculations of the circuit, right? When you feel the bottom of your laptop and it's overheat and you feel all that heat, right? That's all leakage power. It's not going to the next circuit, right? It's going into your hand or into your leg or to your lap or whatever, right? Leakage power. You're trying to minimize that. You don't want it to get too hot and burn somebody, and next thing you know, you're getting sued, right? Like lawsuits are bad. Keeping money is good. Leakage power check. Do that. Okay?
Well, my laptop gets really hot, but it's pretty old.
Oh, okay, yeah.
I'm trying to push it past what we can do.
So voltage drop sign-off text for static current resistance drop, multi-voltage drop analysis, and multi-node voltages and boundary scan mode. So we learned about boundary scan mode. We're able to boundary scan around our circuit to do proper testing. And here we kind of have a multi-power domain design. This is in 65 nanometer. And basically, during the course of operation, you're going to have certain amounts of power consumption in certain portions of the circuit. So this is kind of a view of how it's actually where power is being consumed in certain, how power is being consumed in certain portions of the circuit. That becomes an important, you want to try to spread that out as much as possible. And then that's another power. And here you can see like there's very little red. Red is like too high, but you're starting to get into orange and yellow, right? So here you're actually consuming, you see kind of green, it's starting to get a little more. So these areas are consuming more power versus as if you get to this light areas, it's only consuming 0.7 millivolts, all this area here. So you can see, this is actually a power map, and you can kind of tell whether or not certain aspects of it are the
memory versus the arithmetic logic unit versus whatever other functions happen to be in there. So are the specific portions of the circuit consuming power in what you expect?
All right, so another instance power map is just seeing specific instances throughout the circuit, and worst case voltage map is this one, right? And now, so basically, all right, so let's go to 33 here. So here we're having some sort of instantaneous current with package data, and let me zoom in so I don't think you guys can see here, right? So we're measuring the current consumed at 3 different nodes. And you guys probably still can't see that. So you have one that kind of looks like this, right? So the second one is kind of going like this. And it's measuring. Then the third one is measuring the average, which is the sum of the two. And you see that's kind of in the middle here, right? So basically, it's trying to compare supply voltage ground VDD versus VSS, and it's what's the average being consumed during that of the power at this particular node. Oh, I'm sorry, average current. And so the current relating to when it's being consumed, right? So you can see that ultimately you kind of want your supply voltage to be constant, and you've been going in opposite directions. Remember, current's flowing in towards, trying to flow away from VDD or towards VDD, right? And towards ground or away from ground. So there's your current flowing in opposite directions. So if you balance the circuit properly, it's going to be more or less 0. So that's your goal. Okay, so last thing, physical verification sign-off. The following tasks must be performed to guarantee the manufacturability and functionality of a design. So you've done pretty much everything in this. You've done ERC, you've done layout versus schematic, you've done DRC in this course. Compare. So basically what compare is if you have two circuits and you're comparing them. You have the circuit that you know works, and you have a circuit that you synthesize. XOR, if they're both, if you're for a bit, if you're expecting 0, right? And 0 comes out, and you do an XOR, it's 0, right? If you're expecting 1, and you get 1 from your circuit that you know works, and you get a 1 from the circuit that you're testing, they both come out, the XOR will be 0. So if you're getting a 0 on the XOR all the time, that means your circuit is working properly. If you get a 1, that means you have an instance where either the circuit that works is a 1 or a 0 from your testing, or either 0 from the circuit that you're working and a 1 that you're testing. So XOR testing is checking to be sure that this actually works. This is actually done with even more accuracy by using a voter. So you have 3 inputs, right? And I could just draw it in here so you guys can remember. So you have 3 inputs. And if 2 of them are 0, you're going to get a 0 on the output. If two of them are 1, then you're going to get a 1 on the output. And so what happens is, especially when you're dealing with applications in space, so let's say you're doing have a computer that's going to run on the space station, and we're going to go to the moon or something like that. So you're going to have triple redundancy, and you're going to have output checking. So what happens if one of them breaks? Well, you still have 2 other ones, and you use these majority voters to test to see if 2 or the 3 of them are still working, you're going to get that same result. If it's broken and all 3 of them are still right, it's still going to give you the same result. The only instance that would break down is if you have 2 of them that are broken. So that's a kind of an expansion on comparison checking. And then last, we've kind of covered a lot of this today, mask layer integrity checks. So this last thing, we're going to talk about these soft check verifications here. So basically the idea is that for digital CMOS, you want VDD and ground to be done in couple, right? So that's why it's complementary metal oxide semiconductor. So what you don't want is you don't want any power or ground connections done without, is known as standalone. What that means is you don't want an instance where if let's say you're doing an inverter, right? So you have VDD and where's ground? Excuse me. This would be standalone. So if you somehow have hooked up your circuit or you don't have, so you had your two instances where we're supplying the I/O power pads and then you have your supplying the logic circuitry for your VDD and ground. If you somehow screwed this up, and especially with your N-well and P-well, this is what this soft check is making sure that you've properly laid it out in that manner. And then these last two things we talked about, actually we haven't talked about EMI. So you all, in movies, you've all heard about EMP. You set up this giant EMP and suddenly none of the electronics work. So obviously if you get that level of electromagnetic interference, there's nothing you can do. But you want to stop smaller levels of electromagnetic interference, right? So what we do is we do this EMI sign-off. Electromagnetic interference sign-off is used to drive changes in the clock tree implementation to determine if any EMI affects the board design. So what this is specifically targeting is, we kind of talked about the rat's nest and the clocking tree, right? So especially as you get to smaller and smaller technologies, 22 nanometer, 14 nanometer, you are dealing with more power consumption occurring in the clock tree. If you have some sort of electromagnetic interference affects the clock tree, you're going to affect the entire circuit. So you really need to check before you send it out that this is addressed. And then last but certainly not least, we're going to deal with yield sign-off. Yield sign-off is performed mainly by fabless design houses, which is us, right? And we're going to perform analysis at the chip level, critical area analysis, so we've talked about that. Lithographic simulation and verification process across process windows. We're going to do chemical, mechanical planarization, which is a bit outside the scope of the course. We kind of briefly touched into how I showed you a video at the beginning of the semester where we're actually kind of synthesizing the chip out. So there's a test at the yield sign-off that you do using your tool to actually make sure that when you're actually doing it at the technology that you say, it's actually going to do that. And then last, parametric yield analysis, which is again a bit outside the scope of the course, but you also want to make sure that your solid state devices are, when we're talking about yield in a die, you want to make sure that the amount of, if you synthesize 1,000 chips, you want to get as many of them working as possible. It has to work across the die, so you want to make, this is why all that stuff about consuming power and looking at power instances across your specific chip becomes important, because you don't want to be having all these dies across the place where if you get die impurities or it'll still work. So that's why you want to design that way. So that's chemical, mechanical planarization analysis and parametric yield analysis. Okay. Does anybody have any questions on this? Well, congratulations. You have made it to the end of CMOS VLSI design. You did all this stuff to make something that could fit in the middle of a dime. You have your last lab and your presentations due on Tuesday. Because of your situations, turn in on Thursday. All is understood. I am very, very happy with how you've all done as a class. I've alluded to this a couple of times. Keeping ahead of where you guys were at was quite the challenge. It's a very good problem to have. It's the exact opposite of what you'll get in a lot of classes where you're just trying to drag everybody to the ABET finish line. I can honestly tell you that in the stuff you covered in sections 7, 8, and 9 is not being covered in any CMOS class anywhere. It's like briefly alluded to. I did kind of go to other courses, that are going into this in a lot more detail than what we've covered here, because that's the specific function of the course to say, all right, well, what are the things that I wish I learned when I took CMOS? I wish somebody had actually told me what's actually going on. What is actually in the pad frame? What is actually physically going on in there? These synthesis tools, what's actually being done? What is floor planning? There's there's this floor plan, and it's a floor, and there's a plan, right? So I structured the course around trying to optimize the things that I wish I had learned when I was taking the course and kind of had to learn on my own, and try to optimize the skills that you're going to be using towards when you get a job, right? Because that's ultimately your goal. I do want to kind of hit on this again for the final project, for the final lab assignment. You shouldn't be taking too much time. I know finals are coming, so I don't want you to worry too much about this. I'm very proud and happy of your performance in this semester. Do not spend too much time on lab 3. What I want to see is that you've done the steps to try to get the assignment done. I want to see that when you head in, if you get some sort of weird error messages, that you've made an honest effort to attempt to fix them. And if you didn't fix them, what did you learn in that process? You shouldn't be taking 20 or 30 hours. That's my expectation for this final assignment. What else do I want to say? Oh yeah, I will get my feedback on your presentations back to you by no later than tomorrow. Sorry, I've been out of town these last few days, so I haven't been able to promptly get you that information back. Because of the fact that I know you guys have been working so hard, that's why I considered that approach to the lab fair. Okay. Tuesday, the first 4 groups will present, and then Thursday. One other thing. I think I may have said this in class, but I want to say this again. All right. So when you're doing presentations in previous classes, or you did them in high school, the general idea was, the professor's grading. We don't want to hurt each other. So we're all going to stay quiet. We're not going to ask questions. We're all in this together, right? Okay? Coleman's like, no. Coleman's like, I was the guy who ruined everything for everyone. But I mean, that's generally, you don't get much interaction between groups because of this, right? And people are afraid coming up here. And if there's one thing that I hope you've learned that I consider important, is that failure and frustration should be part of the learning process. Too often we're too afraid to account for I didn't succeed. That's why I have this challenges section in the back, because I want to see how you encountered failure and how you dealt with it. Because I consider that as important, if not more so, than producing a good final product. So for the presentations, the goal is to generate discussion. And you have to understand something, and this is very important. I want this in your head as engineers from here on for the rest of your career. You don't know everything. I don't know everything, right? So you have to be willing to admit that you don't know. So when someone's going to ask you a question about your presentation, it's fair to say, I don't know, I'll look that up. And you guys have the opportunity to go onto Blackboard and interact with each other. Aaron asks me a question. Let's say Coleman's up here, and Aaron's like, oh yeah, you're the guy who wants to do anything. I'll show you, right? Aaron asks Coleman a question. Coleman doesn't know the answer. Okay, that's fine. I'm not going to go, well, Coleman didn't know the answer to a question that PhDs still don't know, minus infinity, right? That's not the way this is going to work. I want to encourage you guys to learn from each other, and these kind of projects, and you guys have done very well. Like I'm sure you've seen from the comments on SemiWiki how impressed a lot of the professionals are with what you've done. And nobody around the country is doing that. And so this next week, you're going to be an opportunity to learn something that no one else is learning. And so I want you to take that opportunity, ask questions, get involved, interact. Because ultimately, a big thing in getting a job is not just having the knowledge that's in here, but being able to get it out of your mouth, right? That's one of the reasons why exams are important. Can you show me that it's in your head and that you can accurately convey it? That's why I have the TGOs the way they are, because I believe that these are the best ways to convey these concepts out. Right? So get up here,
I've done my research on this, and I thought it was really interesting. And you go on your spiel, and you're done. Jason has a question. Tyler has a question. You guys interact. I kind of sit there and just observe, right? Your grade is essentially going to be decided, like by the time you're done, right? So on Thursday, Suprab will be presenting, and then Kevin will be presenting, and there will be pizza. So that'd be good. The pizza is the acknowledgement. I do know that I ask a lot from my students, and the pizza is a way of saying you've worked hard this semester. I acknowledge that, and here's food. In college, what's college all about? Trying to get the free hookup as much as possible, right? So in conclusion, I am very proud and happy with the way you guys have done this semester. I can confidently say that you are the best CMOS VLSI class in the world, and that's something you can wear your hat on. Do I have anything else? No, that's it. Have a good weekend. Does anybody have any other questions before I dismiss you?
Unrelated.
Sure.
If the SemiWiki people ask us a question that we had no idea where they're coming from,
Yeah. Okay.
Just kind of like sitting there like, just stare at you.
like we tried to respond to stuff that was in the scope of our paper, like, hey, that we talked about that in our paper. I see where you're coming from, but some other people asked questions about stuff. We were like, what?
Well, example.
You got it pulled up?
Yeah.
I don't.
This is a really good question. I'm kind of curious what they were asking.
Or the one about asking about argon and neon. That's fine.
Yeah.
Well, two of ours were just, hey,
Yeah. I mean, just.
two of the comments on ours was, hey, come read our paper. We think it's nice.
Yeah. Okay. So that's that is a very common. The first time I went on SemiWiki, somebody wanted me to just read his book. I was like, do you have any feedback on how I can help improve curriculum? Well, I have a engineering economics book. Isn't this great?
Yeah, so this guy asked, would running a computer near 0 Kelvin be more feasible than building an optical computer, one that works with photons and not electrons?
All right, let me. All right.
You guys are doing crosstalk.
All right, okay, so I did the first 2 years of my PhD in research in near 0 Kelvin computing versus optical computing, and the answer to that question is no one has any idea. We don't have an optical computer, and we certainly don't have near 0 Kelvin computing right now, right?
Yeah.
The whole idea, he's kind of hinting on this concept of reversible logic, which is any reversible quantum system was initially posited by Rolf Clausius in 1857. The whole idea is if you have a number of quantum interactions and you can reproduce them in reverse, and you get back to that initial state, you've dissipated 0 Kelvin and you've had 0 entropy gain.
Yeah.
So they're trying to consume as little power as possible. So this is kind of where CMOS ties into play. And what you learned at the beginning is about positive and negative electrons passing through a semiconductor. When you feel heat, that's what happens when you have electrons combine and that energy is just dissipated into the environment, right? So you want to regulate that as much as possible, which is kind of what we were talking about earlier in class, of making sure that you've distributed the power properly, because if you have too many electrons hitting in one area, you can have serious power consumption problem, particularly with wiring and crosstalk. That was the subject of your paper, kind of, right? If I recall. Which paper was yours?
Ours was the superconducting computer.
Oh yeah. So you're at the exact opposite spectrum of that problem. Yeah. That question is way outside the scope of.
That's why I was like, I don't.
It was like,
Yeah,
research.
I think your group had something that was kind of talking somewhere.
Ours is about the power consumption on the wireless,
Right.
What do you call them? Sensors, wireless sensors. But there's a computer that HP is building right now that uses the photon for networking stuff. They
Right.
actually use like a bunch of it. And they were talking about something called a memristor. It's
Okay.
a resistor, I guess, that stores
Supposed to store
memory.
some sort of memory.
Yeah. And I guess they developed it in like the 60s, but they're using it in their computer to replace transistors, I guess, or to replace transistors in memory.
So one of the a good thing for you to remember as you go forth as engineers, if you want to find a new idea, read an old paper.
Someone already did it.
Yeah. So well, I mean, not so much that somebody already did it, but it was an idea that's kind of abandoned. But as you're coming up to a new challenge, you might be able to use it again. For example, NASA's having a real problem. Like we talked about temperature ranges in CMOS, and that you really can't get it working above 300 degrees Celsius. 175 degrees Celsius. Well, Venus gets up to about 300 degrees Celsius. So you're going to excite too many electrons, and you're going to have these collisions. And usually when they send a probe to land on the surface of the planet, the computer works for about 10 minutes. Which when you spend $1 billion sending it over there, it's not very good, right? So they've been trying to use JFETs instead of CMOS because JFETs have a much wider energy band. They're not as efficient, and they take up a lot more space than CMOS, but trying to make it work using JFETs, using an old idea to challenge a new problem. So that's kind of what they did something very similar with the MEM resistors. So yeah, in that case, I don't know what to tell you other than
I just didn't answer.
yeah, no, there's no.
Just no.
Yeah, it's just.
Can I respond? Just no.
Just
Don't speak.
Yeah, just say I like turtles or something like that. So does anybody have any other questions about the feedback they've got? I know one group, fortunately the Beard Boys haven't gotten any comments on there, so I might just have to go on there and comment just to do something.
There was nothing wrong with it.
Nothing wrong with your paper, just say secure core, not relevant to everything. Yeah, I'm a little disappointed in that. Unfortunately, I think yours got buried in the middle of that Moore's Law is the five part.
I got emailed like 6 times on that, like trending on Wiki.
Oh yeah.
Stop spamming me.
Yeah, I have a go-to side thing. Kevin, did you have something you wanted to?
No, I just had a comment about, you were talking about if you, new idea, read an old paper. When we first started working on our research last summer, the very first paper we found for an idea for technology that's barely coming into its infancy was from the 50s.
Right. So let me tell you a dissertation story. Back in my day, we're not a PhD student. So there was this weird debate in reversible computing about whether or not you were permitted to use memory, because somebody had thought in their head that if you had any kind of feedback, you'd have information loss. If you have information loss, you wouldn't be able to retrace all the steps back to that initial state. And one of my colleagues in the lab got a paper rejected because of it, and it broke him. Like he's like, I can't do this anymore. I'm quitting. I'm out. Michael.
Oh yeah, that's like
And really good guy, really smart. And so I was just thinking that kind of picked at my brain and picked at my head, and so I kind of went through this. I actually developed this mathematical proof to show that you could do it. You had to do it in a very specific way. But I'm like, no, in order to do that, I actually had to teach myself the underlying quantum mechanics. Like, okay, so I had to read Ralph Clausius, and then Boltzmann, and then Schrodinger, and then Einstein, and then Richard Feynman, and then well, it's the guy who actually, there was a paper, irreversible in the heat generation process, like it was Landauer, Rolf Landauer. And so I go through all of this, and I prove it. I'm like, I have a mathematical proof, and then I'm looking at the very first paper on quantum computing written in 1980 by Tommaso De Folli, and he has a proof in there in chapter 3 of his paper. We're saying that sequential computing is permitted in quantum computing. And so all of these rejections that people were sending out were not valid. I just proved it in a different way. So I actually sent this guy an email. He's still a professor at Boston University. And he gives me a call, and he's like, these researchers are amazing. He's like French. And his roommate, he was roommates with Steve Wolfram.
So he went on this like 30-minute tirade about how people are not nice to Steve Wolfram. Yeah, I was like, all right. And eventually I got the permission to, I said, well, can I go forth and publish this paper? It's a different approach, but comes to the same conclusion you did. And he's like, go ahead. And I said, can I list you as an acknowledgement? He said, yeah. Well, if you list Tommaso Toffoli as an acknowledgement in a quantum computer paper, it's getting accepted. Like, it's like, oh, I'd like to thank Albert Einstein for his help on my physics paper. No, it's like, oh, Einstein, screw you. Right? So, and now every time somebody wants to publish a memory paper in quantum computing, they cite that paper that I published to get around all these idiots who still think it's a thing. So, you know, old paper, new idea, something somebody did in the 80s, you know. Oh yeah, that comes back to my last lesson for you guys. Just because something is published in a research paper does not mean it's true. Challenge, question, right? Like we were talking about at the beginning of the lecture with the MIT people who figured out how to write an algorithm and a program that wrote papers that were accepted.
That was an exercise in exposing bad journals, right?
Yes.
Okay. So the algorithm, you just use it as you write your paper?
Oh yeah, you're just saying I want a paper on quantum computing, and it'll generate one for you.
It makes the paper.
It makes the paper, and you have to be. The reason why I encourage you to go after articles in certain journals, and if you've and with Kevin at the PhD level, it's go to IEEE Explorer, Google Scholar. There are a lot of really bad journals out there, really bad conferences that will accept anything. My first year, I published 3 papers in a conference, and I thought I was the bee's knees, right? So then I get out there, and it's like 80% acceptance rate. Like, no, that's just you're just taking money, right? And so what's that? What's wrong with that? When people read what you wrote and think it's true, right? And you go, oh, okay. I mean, what I wrote was solid. I just thought, oh, cool. I have 3 conference papers. But you know, I encouraged Kevin to go to the Design Automation Conference for his work, so which has like a 20% acceptance rate, which is a little lower than normal. It's a very competitive conference. But Kevin also found out today that he is a recipient of the A. Richard Newton Scholarship Fund, and so he's getting his trip out to the Design Automation Conference paid for. I got a couple of. We are not amused.
I just have to tweet the whole week.
Yeah, Kevin gets to tweet, but a lot of the people I met. Daniel Nenny, the semi-wiki guy, out at the Design Automation Conference last year, and they actually able to fill up the San Diego Convention Center, the same one that they use for Comic-Con. Yeah, Comic-Con. They fill it up with vendors and people giving papers, and it's nuts out there. But it's actually a rather prestigious scholarship, and it's very highly competitive. So that's very good on Kevin for getting it. And I also got it when I was a first year. No, I mean, but it's good because it makes connections. But more importantly, because Kevin's done good work, and I want people to know that. It is 12:09. Is there anything else that you guys wanted to ask about? We got 6 minutes before I'm legally required to dismiss you. No? All right. I will get my feedback to you by tomorrow on the presentations.